Look at the sheer size of a facility like this. Moving data from a remote sensor to a centralized controller often means pushing a signal across thousands of feet of wire. That data usually originates at a field device, like this pressure transmitter, which measures process variables out in the elements. But getting that measurement back to the control room means traversing a highly hostile electrical environment. Heavy machinery, large motors, and variable frequency drives constantly blast the area with invisible electromagnetic interference. If we try to transmit this pressure data using a standard 0 to 10 volt signal, we immediately run into a physics problem. This diagram illustrates a voltage source pushing a signal through a long wire. Because the wire itself has natural series resistance, Ohm's law dictates that we lose energy along the way. By the time the signal reaches the controller, that line resistance has caused a voltage drop, corrupting the original measurement. To accurately read a voltage signal, the receiving controller also needs a high input impedance. That effectively turns our thousands of feet of copper wire into a massive antenna. That antenna easily picks up all the ambient electrical noise from the factory floor, which layers high-frequency spikes right on top of our already degraded signal. Between the signal decay over distance and the absorption of stray electrical noise, voltage signaling fails in heavy industrial applications. To solve this, process engineers rely on the 4 to 20 milliamp current loop. This method leverages a basic axiom of circuit design. In a closed series circuit, the electrical current is exactly the same at every single point. The transmitter is an active regulator, pushing electrons at a precise rate. The source and receiver ammeters read the exact same value. If we stretch the cable, adding massive line resistance, the transmitter adjusts output voltage to maintain the exact same current flow. Because current loops operate at a very low impedance, they don't act like antennas. Any stray electromagnetic interference bouncing around the factory lacks the energy to alter the physical flow of electrons. Current loops inherently solve the two greatest threats to industrial data: distance degradation and electrical noise. The specific scale of this loop, 4 to 20, follows a 1 to 5 ratio. That math inherited the legacy of the old 3 to 15 psi pneumatic tubing used in early factories. When those pneumatic tubes were replaced by early electronic control rooms in the 1950s, the first standard was set at 10 to 50 milliamps. The bulky magnetic amplifiers of the era required at least 10 milliamps just to operate. The invention of highly stable silicon transistors allowed engineers to drastically scale down those power requirements, arriving at the 4 to 20 standard we use today. But why establish the ceiling exactly at 20 milliamps rather than 30 or 50? This scale maps out the human safety factor. The Occupational Safety and Health Administration defines 50 milliamps as the threshold for severe shock and cardiac hazard. Capping the operational limit at 20 provides a strict safety margin for technicians working on live wires. It also enables intrinsic safety for hazardous environments, like chemical plants and oil refineries. The energy required to ignite an explosive gas is proportional to the square of the current. By limiting the maximum flow, the total energy in the loop stays so low that even a dead short circuit cannot generate a hot enough spark to trigger an explosion. The 20 milliamp ceiling is an engineered boundary determined by the physics of human safety and combustion. Looking at the bottom of the scale, the intuitive assumption is to start at 0. It seems logical that 0 pressure in a pipe should equate to 0 milliamps of signal. But if 0 milliamps means 0 pressure, how does the control system tell the difference between a true 0 reading and a hardware failure? A severed cable, a blown fuse, or a completely dead transmitter all cause the current to drop to 0. In a high-pressure system, a severed wire during a peak event would falsely tell the controller the pressure is safely at 0, leaving operators blind to a mounting disaster. This diagram compares a 0 to 20 loop on the left with a 4 to 20 loop on the right. If we cut the wire on both, the current collapses to 0. The 4 to 20 controller instantly recognizes this drop as a fault, while the left dangerously registers 0 pressure. This self-monitoring logic is formally standardized across the industry under the Namor NE43 specification. It dictates that any signal dropping below 3.6 milliamps is officially classified as a low fault condition, which automatically triggers safety interlocks and alarms. Offsetting the baseline to 4 milliamps transforms a blind stream into a continuous, self-monitoring diagnostic network. This live zero solves a secondary infrastructure problem out in the field regarding device power. Running separate power and data cables to thousands of instruments is expensive. Instead, engineers use two-wire loop-powered transmitters, which use the exact same pair of wires for both signal and power. Here we see how the transmitter utilizes that continuous 4 milliamp baseline. Even when the process measurement is at absolute zero, there is enough current flowing through the loop to run the device's internal microprocessor and sensor arrays. Modern transmitters are incredibly efficient, designed to operate on as little as 3.5 milliamps, leaving a safe buffer above the fault detection threshold. If the loop dropped to zero for a zero reading, the field device would instantly shut down. The 4 milliamp offset is a strictly necessary mechanism for delivering power. This continuous, closed-loop system creates a paradox when technicians need to verify calibration in the field. To measure electrical current with a standard digital multimeter, you have to insert your meter in series with the circuit. But physically breaking the wire in the field to attach those multimeter probes instantly drops the entire loop current to zero. That momentary disconnection is instantly detected by the controller as a fault, triggering the exact plant shutdowns the Live Zero was designed to execute. The solution is a non-invasive hardware bypass. A standard silicon rectifying diode is permanently installed directly in series with the transmitter loop. During normal operation, the signal simply flows through the forward bias diode. This adds a negligible voltage drop of about 0.7 volts, which the loop power supply easily overcomes. This simple piece of silicon creates a permanent diagnostic gateway. When a technician needs to read the signal, they simply connect their multimeter probes in parallel directly across the diode's terminals. This exploits a massive resistance differential. A multimeter has extremely low internal resistance, under 0.5 ohms, compared to the diode's 10 to 100 ohms. Current takes the path of least resistance, entirely redirecting through the meter. You get a live reading without breaking the circuit. This troubleshooting exploit relies entirely on the 4 milliamp Live Zero. A silicon diode requires about 0.6 volts of forward bias to conduct at all. It physically cannot operate if the current drops too low. If this were a 0 to 20 system, any reading below a half milliamp would lack the energy to forward bias the diode. The measurement would fail, showing zero current even when a small signal was actually flowing. The 4 to 20 milliamp loop survives as a perfectly balanced ecosystem where physics, diagnostic safety, and power distribution seamlessly interlock.